I'd like to proceed now with a lecture with chapter 6, which is about Huckel theory. Huckel theory is a beautiful illustration of how the principles which we have introduced and discussed can be applied in a numerical fashion, such that you can predict action numbers and energies for comparison, for prediction of trends, let's say, among different molecular species. It is one of the lowest level kind of theories. As such, it is rather of deductical usefulness than of practical usefulness. And the idea is that you can see sort of live and in practice how the secular equation, for instance, and the various eigenvalues and the wave function coefficients can be calculated in a meaningful way, right, for larger systems, so systems with multiple atoms and of obvious relevance to chemistry. So up to now, you could object to this course in the sense that so far we did not go beyond the diatomic, and of course chemistry is much richer than that. And so Huckel theory allows you now, for the first time and being fully consistent, building on what we discussed so far, to go beyond and consider larger systems. So this course, as I said last week, this course I will teach using a couple of slides I prepared. So I'll be sharing those, and I will not use the iPad. Now, this is a very different way of teaching, obviously, than writing things down. So the typical risk is that I'll progress, I'll advance too fast. So if that happens, please do not hesitate to stop me. Maybe just if you don't want to switch on your microphone, type something in the chat window. Now, for me, it's difficult to read the chat while presenting, so I would ask Mr. Trestman to monitor the chat, and in case there's a question, he could read that question and simply interrupt me, please. Thank you. So let me share the slide. And I believe I have a possibility somewhere to have a pointer. I don't know, have you used pointers in Zoom?
No, I've not.
But I thought there was some option. Maybe I'm wrong.
Usually the options are contained in that that bar. I don't have access to it, but you do.
Where are they contained?
You know, the actions bar that you can kind of drag around when you're the host of a Zoom meeting that can contain screen sharing information. Usually in there, that's all of the. I can't access it or see it in this case.
Right. some advanced sharing options. All right, let's try like this. Would be nice.
If not, I can see your pointer as is.
All right. Try to make this larger though. All right. Can you see my pointer now? You can sort of find things. Okay. All right. All right. Yeah. So this is chapter 6. This is image of Erich Hückel. So he was one of the key figures in one of the founding fathers of quantum chemistry, if you wish, right? So he lived at an age when the field started to emerge, and he was at the end a professor in Marburg, a city in Germany, and he was quite a character apparently. So according to Felix Bloch, when he was a student, he pestered his friends to write poems about their professors, and they made a poem for Schrödinger, which went as follows. So this in German: Gar manches rechnet Erwin schon mit seiner Wellenfunktion, nur wissen möchte man gerne wohl, was man sich dabei vorstellen soll. So you see, as scientists, we can rhyme, but it's not really Shakespeare. But anyhow, so the key of this poem is, of course, true, right? What it's hard to imagine what these wave functions should be, in particular when you grew up in a classical sense with a particle worldview, and so this is what this poem nicely expresses. Now, I said in the introduction that Huckel's theory is a very low-level method, and it's typically not used anymore to make predictions in the more advanced contributions, scientific contributions of these days. And this is because of some of the very severe approximations it applies, and we will come to that later. But extensions of Huckel theory are actually still in use. And so they are listed down here. This is called extended Huckel theory. This is a theory that includes pi and sigma orbitals. So for those who don't know Hückel yet, Hückel only works for pi electrons. You can extend it to also include sigma electrons. And that, of course, makes it much more powerful. Then you're not restricted to planar molecules, for instance. Even more sophisticated method is the so-called Pariser, Parr, and Popel method. This is even less approximate and more accurate. And in particular, there's a third method I should mention, which is related to the fact that most of you are in Basel right now. So Edgar Heilbronner, who used to be a professor of physical chemistry in Basel, he applied Hückel's concept to Möbius structures. I suppose you are aware of Möbius structures, and so these are molecular rings, for instance, that are folded such, right? They are twisted once before you close the cycle, such that you have a Möbius structure. And the Möbius topology then is interesting because in the limit of an infinite radius, this is still planar. And so you can ask what happens then to Huckel theory. And Edgar Heilbronner investigated this. So what is Huckel theory then, really? I mean, it's a useful semi-empirical method to estimate pi electron-electron effects in planar molecules, okay? So we are considering only the pi electrons. So this is an approximation, right? You cannot do this in principle, right? You cannot say I'm looking only at one set of electrons or another. They are indistinguishable and they all interact, right? So this is strictly speaking illegal, but you can approximately, of course, you can do this, right? So roughly speaking, right? So this is on the level as saying on planetary motion, you assume that the entire planet Earth is a mass point, right? That's a horrible idea if you live on Earth, but on the larger scale of things, comparing galaxies and whatnot, that might be a reasonable assumption, right? So you always have to provide the context, and you have to consider the context when you discuss the value or the usefulness or uselessness of any such approximations, okay? So this is one of the key assumptions, and it is quite crude, but if we can stick to planar molecules, it turns out, and especially if there are not many heteroatoms, and if you have only double bonds and in regular, let's say, angular coordinates between the atoms, so if the atomic environments are very relaxed, right, in the typical sp3, sp2, or sp kind of configuration, then you can actually get quite decent results. Now, 1 second, I have to correct myself, not sp, okay? So the sp orbitals are actually, there's some pi orbitals that are in the plane and not perpendicular. So we'll come to that later. And so this would be a huge problem for Hückel. So don't treat triple bonds with Hückel, right? So only double bonds and planar systems, in particular aromatic cycles, right? Now this is, of course, aromaticity is a cherished concept in organic chemistry and elsewhere. And so a theory which only explains aromaticity is already quite useful to the chemist. So this explains a little bit also why, despite all these severe and crude approximations, Huckel theory is still so popular, okay? So even experimental chemists often have a very good understanding of chemistry in terms of Huckel theory. So this is really a sort of level of understanding of chemistry, which even if you don't care about theory in the future, you should really, if you want to be called a proper chemist, you should really make sure you understand this chapter very well, okay? Okay, so how does it work? The first thing is that you say, well, the wave function for my pi electrons, this psi pi, for all my pi electrons, okay, this wave function is actually a product of molecular pi orbitals, okay? So I presume you have some idea of how a pi orbital, a molecular pi orbital might look like, right? Now you have many of those, right? For all your pi electrons, you can have these pi molecular orbitals, and the total wave function is simply the product of these guys, okay? And each of these molecular orbitals is the solution to a one particle Schrödinger equation, this one here. Okay, so once you solve this for your n electrons, here's the small n, right? For your n pi orbitals, once you've solved this, you can then take the product of all these molecular orbitals, and that would be your total wave function of your system. This is an Ansatz, okay? This is it's just he dreamt this up in the morning, okay? So what is the result then? We can say our total Schrödinger equation, right, consists of the sum of these individual single particle Hamiltonians, and they are being applied to the product of these MOs, and they will generate our eigenvalues, and then the total energy of your system is simply the sum over the eigenvalues. Okay? So if somebody asks you the total electronic energy of your pi system, we're talking about the pi system, right? You still have to add the sigma electron interactions too, right? This is given by the sum over the eigenvalues of your pi molecular orbitals. Okay. So here comes a second Ansatz. So there's a cascade of approximations, right? They're all chained to each other, right? This is, of course, the amazing thing of such a theory, right? That the specific combination of such approximations and ansatzes, which still works, right? You could imagine at any point here, at any time you make such an ansatz, the whole thing can break down. Right? So the really subtle thing is that Hückel managed to negotiate all these approximations such that still something reasonable can come out. So that's truly impressive in some sense, right? So the next ansatz is that any one of your pi MOs, which we call small phi here, is again, you can express it, you can series expand it, right? And this is something which we discussed ad nauseam in our second chapter. You can series expand this in a bunch of basis functions. And in this case, we choose as basis functions atomic 2p orbitals. All right? Those you learned in high school, you know how they look like, right? It's these dumbbell-shaped functions, right? This, on every atom that contributes a pi electron, you put such an atomic orbital, okay? And then you expand in there. That means you need some coefficients here. So, for example, the molecular orbital I for some MO, right, is the sum now over these two p orbitals, these atomic 2p orbitals, on every atom capital I. Okay, and you sum them all up, and each one of these guys gets a coefficient, right, which of course depends on which atom you're talking about. So it depends on your capital I. And of course, it depends on the target molecular orbital to which they are supposed to contribute, right? So you can imagine you have a couple of carbon atoms. Let's say you have 2 carbon atoms, right? And there's one molecular orbital where the atomic p orbital of this one contributes a lot, right? And there's another one where it contributes less, let's say. Right, so then the C coefficient for this atomic orbital can change, right, for these 2 target molecular orbitals, right? And the same thing on this carbon atom, of course, right? So you have number of atoms times number of states, right? The states are given here. You have n, for n electrons, you have n states, right, with eigenvalues here. And each of these states has contributions from each atom according to this linear expansion. Okay, we are talking two indices now, the small I and the capital I. Now, to make things more pretty, we like to change the capital I, which we have here for every carbon. We want to generalize this into a small j. There might be heteroatoms, non-carbon atoms that contribute 2 electrons to the pi system. There might be other atoms that contribute none to the pi system, right? So you don't want this to be contingent on carbon only. We might also want to consider charge species, right, where you removed an electron. So let's not restrict ourselves to carbon like in this central equation here. We can generalize this much better. Now we use J to run over your atoms, right? J is the atomic index, and I, the small I, is to run over your states, okay? So you immediately see there is an n by n kind of matrix that you can make up from these coefficients here, right? And then, of course, so for n pi electrons and n atoms, we have the problem of finding the values for these coefficients, right? If we have these values, right, then we know our molecular orbitals, and then we know our wave function, okay? As you might recall from the variational principle, we get the energies before the coefficients, right? So on the way to getting these energies here, these eigenvalues from which we can get the total energy, on this way we get the unknowns which are required to solve for these coefficients. So things are a little bit like flipped around, right? You use these eigenvalues here from your Schrödinger equation. You use these eigenvalues to identify the wave function. It's a bit funny, right? You know the Hamiltonian operator, and you first calculate these eigenvalues, and then you know those, and then you look for the function that obeys that Schrödinger equation, right? You look for the eigenfunctions that do that. And these eigenfunctions are given by these coefficients, okay? So I hope this is clear so far. Now we do what we already discussed. First things first, let's normalize, all right? So here we go. Our molecular orbital of state I should, the self-overlap should correspond to 1. Now you simply substitute your nice little expansion here, right? This you know already. We can pull out the double summation, and the coefficients, they do not depend on your integral, and you're left with this overlap integral between atomic 2p orbitals, okay? Sitting on atom J or atom K. That's what this is. Now, if they sit on separate atoms, and this is one of the assumptions in Hückel, you actually presume that they do not overlap, okay? So in other words, this is a Kronecker delta, and hence the whole thing kills one of the summations, right? And you're left here with the norm of coefficient J, and this means that all your coefficients, when you take their norm, right, this has to be 1, right? So this is one of the conditions we have on our coefficients, right? So this is in Huckel theory, this is a very important step, because without this normalization, it's not a fully, you will see this, it's not a fully determined problem, okay? So you really need this additional normalization constraint to solve for your coefficients. You cannot uniquely define your coefficients if you don't have the normalization. There's a random scaling factor in front of it, if you wish, if you don't want to normalize, right? Which you could, so for instance, the shape of your orbital still looks the same. If you scale up everything with a random number, doesn't matter. But if you want to compare the different orbitals, then it would be tricky. All right, so this is the ansatz, right? So you see up here is the table of contents. And we go now to the Ritz Theorem, or also known as the Variational Principle, right? So Ritz is another name for the Variational Principle. And we will use this to get the coefficients together with the normalization, right? So you recall that we have our Schrödinger equation. If you multiply from the left with your orbital psi I and you integrate, right, then you find that your eigenvalue times the self-overlap must be the expectation value of the Hamiltonian. Now we substitute our expansion in here, right? So on the left, you see what we already had. You see, yeah, right. And on the right, you also substituted this, but you have the Hamiltonian. So this is in complete analogy to chapter 3 on the variational method, okay? So if this goes too fast for you, please go back and have a look again at those. It's just that in this case, our series expansion is well defined, right? So we did it more in a more general fashion in the variational theorem. Here, our f's, our small f's, really correspond to atomic p orbitals, right? And our index j runs over the different atoms in the system. So you can see in the next step what we already saw before. You can pull out the summation and the coefficients also here. And now the Hamiltonian has to operate on the atomic orbital k, right? And this expectation value, this is what we call our Hamiltonian JK element. So this is sort of the energy, right, of atoms J and K interacting through their basis function. And it gets scaled by this product of these coefficients belonging to atom J and K, which correspond to the eigenstate I, okay? So you're seeing 3 indices now, right? Atom J and K interacting with each other and contributing to the state I, right? So 3 indices. Similarly, on the left, you also have these coefficients, only it's not the real energy, it's just the overlap, right? And in front of the whole thing, you get then the eigenvalue of your state. Now we apply the variational principle. So up to equation 10, this was basically just Schrödinger's equation and insertion of your series expansion, right? And then we defined our overlap integrals S and H, which carry the indices J and K for the atoms J and K, right? This means it's a matrix, right? An n by n matrix, right? Which you can populate with these integrals. And very important, this matrix does not depend on the state. For every state, it's the same matrix, right? What changes for each state are these coefficients, right? And this is the reason why, at the end of the day, we can get the eigenvalues without solving for the coefficients. Only once we want the wave function, we will need the coefficients. So let's do this. Let's use the variational principle. You know this, right? We did this in chapter 3. So now we differentiate with respect to the third index m of the coefficient of state I. Okay, so that's basically a third atom you're playing. This is your before we had indices j and k for atoms j and k. Now you come and you say, for my state I, what happens if I vary the coefficient for state I sitting on atom m? Okay. So so we did this derivation, right? So you have this expression equals this expression. This term here. So if you differentiate here from the left, right, then you get dEdC by product rule times the double sum, right? But dEdC is 0, right? So then you're left only with this, and that must be equals this. All right, now you have to differentiate these coefficients, and we did this for the variational theorem. Again, it's in complete analogy, right? As I said in the beginning, Huckel theory illustrates what we discussed so far, right? So you shouldn't be surprised to see exactly what we did, right? It's exactly what we discussed and what we derived. And you find at the end of the day this expression, which should look awfully familiar to you, right? It's a system of equations. And you see now we sum here for atom K, right? You sit on atom K, you sum over all other atoms J, right? And you contribute to state I, and these are the coefficients sitting on each atom J contributing to state I. Right? Now, we know that this expression, right, this is the equation for an atomic p orbital K, right, as we said, the atom K, right. We know that we can do this, of course, for each atom, right. And so this holds for atom K, but you have n such equations, right? So 17 and 18 is the example of the molecular orbital I, just one molecular orbital, pi orbital, right, of ethylene, okay? So here is the expression for your first atom, right? So this is the atom 1 here, right, 1. This is K equals 1, right? And then you have the contribution from the second atom, K equals 2, all right? And both of these atoms contribute by interacting with the other atom to state I. Right? So this is nothing else than basically n homogeneous linear equations, right? Homogeneous means they must sum up to 0 for the molecular orbital phi with the eigenvalue ei. And these n coefficients can be determined up to a multiplicative factor, and we can determine this multiplicative factor through the additional constraint of normalization, right? Now we can write equations 17 and 18 in general in a single line by using matrix notation, right? So for any n by n matrix, right? So for any system with n electrons, right? You can write a matrix like this for state I, right? Remember, this is just one state. Right? It's So if you have multiple, if you have n electrons, you have this equation n times, right? For n different states. Right? Okay, now remember, there's this non-trivial solution only if, that means the coefficients being non-zero, right? So if all coefficients are 0, then this is true, then equation 19 is true, but that's a trivial case. You don't care about these coefficients. They give you the magnitude of the wave function. If the wave function has a magnitude of 0, you don't have electrons, right? So that's a silly thing, right? And that silly things we call trivial. If that is true, right, that these coefficients are non-zero, then the determinant of the matrix before has to be 0. Okay, and that implies our secular equation, right, or the characteristic polynomial. So we know that this determinant must be 0, right, and so you get this kind of a matrix, right, of which you have to take the determinant. And this is a polynomial, this determinant, right? It's also known as a characteristic polynomial. And this means you have the job of finding the n roots for which this is true, right? And these n roots correspond to the n eigenvalues of your states. And this is what I said in the beginning, right? That it's a bit funny, but here these eigenvalues, we get them before we get the wave function, right? So it's not as if naively you could assume, okay, give me the Hamiltonian, that's my system, then I get somehow my wave function, then I apply my Hamiltonian to this wave function, outdrop the eigenvalues, right? That's how you would typically, often you get questions like this in high school, if you're in the introductory math courses, you get some function and some operator, and then you're supposed to get the eigenvalue. And so you apply the operator to the function. In this case, we determine the eigenvalue first, right? And then we solve for the coefficient. So this means we can, by finding the roots of this matrix, we get the eigenvalues. And then we use these eigenvalues in equation 19, right? So you get n eigenvalues, and then you have to solve n times equation 19, where you know everything except the c vector. And so you can get n c vectors, and they give you the molecular orbital. All right, so we are nearly 11 o'clock. I'd like to take a little break here. I hope this was slow enough. It's always the danger to go too fast here. I hope you could follow every step. If not, type your questions in the chat during the break. I leave this slide here on during the break if you want to look at it. And of course, we are recording this, so you will find everything on YouTube later on if you want to revise these slides in more detail. I hope this is slow enough and you could follow. Again, there are a couple of tricks, right? How to digest all of this. Do keep track of your indices, right? Your indices are atoms J, K, and M. Your states are I, right? And Hückel is so nice. If you ask how many are there for each of these 4 indices in total now, in total there's always n of those, okay? So you have n, you have n states, and you have n atoms J, and n atoms K, and n atoms M, right? All right, let's have a break and let's resume.
Briefly, Anatole, Laura
Yeah.
asks if you could upload these slides on Atom, which is the...
Yeah, this is certainly also possible. We try, but you'll find them on YouTube too. Right? All right, let's resume at 11:15. Thank you. Okay, it's 11:15. Let's continue with our lecture on Hückel. So we covered the ansatz, okay? And we covered the application of the variational principle and the resulting secular equation, which allows us to solve this problem. Now, I have a couple of examples here, but first I'd like to briefly discuss the approximations which we do, okay, when using Huckel's theory. There are multiple approximations, which we said in the beginning also, but in the solution as it manifests itself in your calculation, these approximations are represented by what we do with these integrals. In particular, we consider the HRR integral. So the diagonal of this H matrix, right? These are the interactions. This is the Hamiltonian acting on the 2p orbital of atom R with the, you take that expectation value, right, for that same atom. So it's some sort of self-interaction, right? And within Huckel theory, we assume that this is a constant. We call it alpha. And we also call it the Coulomb integral, because it's a Coulombic interaction mostly that we use here. This is, we assume that this is the same for all atoms that happen to be the same chemical element. Okay, so all carbons have the same alpha, all nitrogens have the same alpha, all oxygens have the same alpha, no matter where you are in your molecule, right? No matter which system you're talking about. Is it a diatomic or is it a giant protein? Is it in a graphene sheet or is it in a Buckminster fullerene? It doesn't matter. We always presume that this alpha is the same, right? So it's something like the nuclear charge, right? And it's just a parameter that does not change. And that is, of course, if you wish, it's outrageous to assume that, right? Of course, your chemical elements have different properties depending on the environment, and so this is being neglected here. Now, it can be a very plausible approximation if all atoms are symmetry equivalent, right? So imagine the 6 carbon atoms in benzole, right? They are all the same. So then this is a good idea. But just go to butadiene and you have 2 kinds of carbon atoms, right? The one at the end and the two carbon atoms at the ends and the 2 carbon atoms in the middle. Or imagine the carbon atoms in purity, right? Due to the nitrogen, they have you have symmetry breaking, right? And so they should have different alphas in principle, right? But in Huckel theory, this is assumed to be just one. Now we will have some alphas for the various atoms in this matrix, right? And you can then express the solutions in terms of these alphas. You don't actually need to know them, right? So you need to find your roots, your energies, and you express them, these eigenvalues, in terms of alphas, right? So that's really, you keep these alphas implicit. They're always the same, right? If you express your solutions in these alphas, it's more elegant, and you could actually adjust the alphas to match, on average, a bunch of experiments you have or something like this. But this is also something that often adds to the confusion. So we can give you some values for the alphas, but in principle, you should first express the solution in terms of alphas. Then you have the interactions between neighboring atoms, right? The Hamiltonian interactions. So the off-diagonal H, the off-diagonal elements in this H matrix, okay? What about this? This is presumed to have the same value beta for any pair of neighboring atoms. So any of a certain chemical element combination. So beta for carbon-carbon, no matter where these two pairs sit, they have the same beta. So if you reconsider pyridine again, take the two carbon atoms next to the nitrogen, or take two carbon atoms opposite to it, we presume they have the same beta, right? So that's also an approximation, right? And of course, also then for carbon nitrogen, you would have a different beta. For nitrogen nitrogen, you would have a different beta. For nitrogen oxygen, and so on and so forth. Any combination of chemical elements would have a different beta. But it does not matter where it sits in your molecule. Furthermore, we presume it only works for nearest neighbors, okay? So that means in your H here, if the index goes through neighboring atoms, right, not just randomly for your system, it means that you only get the diagonal, the elements next to the diagonal, they contain the betas, and then atoms that are further away, they don't contribute, there's nothing. Right? We presume they are too far away to interact, okay? So they vanish if you go to first neighbor and then second neighbor, right? You already presume they don't interact. So very, very rapid decay. It turns out in practice, this is actually not a bad approximation, right? Because there is some sort of nearsightedness in the whole business of quantum chemistry. And so you don't need to go so far typically, right? So this is typically not a bad approximation, and an experimental estimate of this error you make here is on the order of something like 75 kilojoules per mole, right? This is still substantial, but it's not gigantic, right? So this is not larger than a chemical bond, right? A chemical bond is roughly 100 kcal per mole, a single bond, right? So that's something like 400 kilojoules per mole. Right? So you're not making an error on the order of the scale of a chemical bond here. It's less than a quarter of that, right? Now this integral also has a name. It's called the resonance integral, okay? So these are well-established names, right? And people like to give names to these quantities. The symbols are, so Coulomb integral and resonance integrals, because the respective symbols are alpha and beta. All right, now we come to the worst, the crudest, the most severe approximation made in Huckel theory. But it's a very important approximation. The method would become much more complicated. You couldn't do it with pen and paper. We didn't have this. So we really wanted for simplicity reasons. But physics-wise speaking, this is outrageous. This is a crazy one. And in particular, it's the assumption that our overlap integral is orthonormal, right? So this is not at all true, right? If you presume that on two neighboring carbon atoms in a typical bond length, that they are Slater orbitals. So e to the minus r, this kind of shape, right? They overlap with something like 0.25, right? So they share something like a quarter of an electron. That's incredibly much energy, right? That amounts to that. This is the overlap integral. And so this is the most severe approximation, right? So the 2p orbitals of two adjacent atoms really overlap much more, very substantially. And so to presume that there's zero overlap, right? They're basically so localized on each atom that there's zero overlap. This is craziness, right? And you know this also from the previous courses when you already in the H2 case, you discussed the H2 plus bond or things like this. You discussed the overlap between two neighboring atoms, right? When they form a bond and so on. So this is really a very crude assumption here, right? This is a kind of assumption, right? If you go around in general and you tell people you're assuming this, then you might fail at your chemistry degree, right? Adjacent atoms have to overlap, otherwise they can't share their electrons. It's outright silly, right? But for numerical reasons within Huckel theory, we assume that, right? All right, now let's go to an example, right? So this is ethylene, and we can write down the secular determinant immediately with the definition of our nice integrals, right? See this thing, right? So again, this was our ethylene, right? We take out our prefactors here, right? And form that matrix, right? For which we have to have the secular determinant, right? And then we say the S21 here is 0, right? So this one has to die. The S12 is 0, has to die, right? That's the horrible approximation we are making. The overlap is just the Kronecker delta. So here it's just 1 and 1, right? So on the off diagonal, we don't have any eigenvalue left. We killed it off, right? This is why the equation becomes so easy then, because we kill off the eigenvalues from the off diagonal terms, right? It dies. And so it's only left on the diagonal. And then on the next to diagonal term, we have our beta, right? The Hamiltonian 1, 2 and the Hamiltonian 2, 1, right? And that's what's in this bracket here. And of this thing, we have to take the determinant, right? So that's what's written here now, right? Understood? That's how we arrived here. So with the approximations on the previous slide, your secular equation for ethylene looks like this. So this is a 2x2 matrix, right? This gives you a quadratic polynomial, right? So there should be two roots. There should be two possible eigenvalues, right? These are the two states, right? So we have two molecular orbitals. And so we have the determinant is this one times this minus this one times this, right? So that's what you see here. And that thing has to be 0, right? And so if you say that one eigenvalue is alpha plus beta, right? And then you insert it here, right? Alpha plus beta, and alpha minus alpha is 0 plus beta squared minus beta squared is 0, or minus beta squared is also 0. So either plus beta or minus beta, right? The alpha is just the offset here, right? Okay, so these are the two eigenvalues, right? So you can center it at alpha. One is above by a size of beta, and the other one is below by a size of beta. Okay, that's the meaning of these guys. And now the question for the energy is that we should sum up these eigenvalues. Okay, but here is a tricky one, a little trap in equation 22. You don't naively sum up alpha plus beta plus alpha minus beta, right? That would be just two alphas. But that would be silly, because each molecular orbitals can be occupied twice by two electrons, right? So in total, you have 4 slots, if you wish, right? Now, where are the electrons going to go? Is one electron going to go in the lower orbital and the other in the higher? No, of course, they are both going to go in the lower, in the lowest molecular orbital. So you have to remember the Aufbau principle by Hund, right? You fill up first the lowest lying levels, right? So the lowest lying level, the one with the most energy, right, is this one. Now, there's this convention, right, in Huckel theory that you put the plus beta, you assume to be the lowest one, the lower one, right? So the energy axis is sort of flipped, right? This is where your two electrons go, and hence the energy, if you wish, alpha has a negative sign and beta has a negative sign, right? So that's how it's meant, right? So the more alphas and betas you collect, the lower you will be in the energy, okay? This means then that both electrons go in there, and you sum up for the two electrons in the lower state. So the HOMO has to be counted twice, right? And the LUMO, the unoccupied orbital, does not contribute to the energy. There's no electron sitting in it. So your total energy is simply twice the HOMO energy. Okay. So that's the energy of the 2 pi orbitals sitting in ethylene. Now we come to the question, what do the orbitals look like? Yeah. So we have 2 orbitals, right? So we have to solve 2 sets of equations. Okay. Now, the first is to say, so we go, let me check that. So we go, we have to go back here, right? So we put we have this equation, this kind of equation, or this kind of equation here, right? And now we need to find the 4 coefficients, right? One for the 4 coefficients which we need for now what am I saying? Sorry. You have 2 coefficients for each state, right? This is for the first state, right? This is one equation for the 2 coefficients, and there's the second coefficient equation for the same 2 coefficient of one state, right? So we have 2 equations for the 2 coefficients for each state. So here's coefficient 1 and coefficient 2. It must be 0, right? This coefficient 1 and coefficient 2 must also be 0. Right? Now we can put in our, so these are the two equations, right? And now we put in our two eigenvalues for the two states, okay? So this results in C1 being either the same as C2 or being of opposite sign, okay? And from this you can already imagine, right? You imagine you have a p orbital on one atom and the other one is on the other atom, right? And now they have the same sign, and in the other case they have the other sign, right? The opposite sign. Right? This is what's happening. Right? This is how the two states differ, right? So this means your HOMO eigenvalue has, remember, minimal nodes. The more nodes you have, if you change sign, you have a node, right? Now remember the harmonic oscillator. The more nodes you have, the higher the energy, right? So this means the one where they both have the same sign, this must be the HOMO, okay? So same sign, you can factor out C1, F1 plus F2. In the LUMO case, F1 minus F2. Okay, opposite sign on your atomic orbitals, right? Now, what are the coefficients in absolute numbers? Now we need to make sure we impose our normalization. One,
Right.
Yes?
About the functions, what do they represent here? I mean, where did they come from this whole calculation?
The function phi here?
No, F1 and F2. Are they alpha and beta or?
These are our basis functions, right? So we said in the beginning, I'm sorry. Where is it? This was here, right? These functions F, right, are our 2p shaped atomic orbitals. Okay, remember the hybridization state, S, 1s, 2s, right? 2p, right? Does it make sense?
Yeah.
So these orbitals, right? They are, so if your plane, your molecular plane is in x and y, right? It's the pz, the 2pz orbital that stands out. Looks like a dumbbell. You must have seen them previously, have you not?
Yeah, no, that's not the problem. I think I just didn't quite catch how these correlated, but it's just the signs that we kind of were able to
Exactly.
put in.
Look at this. Look at this, right? You put your molecular orbital is the sum, you sum here over the atoms, right? Just the sum of these 2p orbitals, everyone sits on a different atom.
Yeah, it makes sense now. Thank you.
And the coefficient assigns the sign of this 2p orbital and the magnitude, right? Like you can scale them up and down, right? And that depends then really on which state you're addressing here, which state, small I, you're addressing. Right? Okay, thank you so much for your question. I'm sure this helped clarify also for many others what we are doing here. All right, so now we want to know the magnitude of the whole thing, right? We figured out the sign, but not yet the magnitude, and we have our normalization condition. Here it comes, right? One must be equal your HOMO, your inner product of your HOMO. Okay. Well, we simply insert our HOMO, right? Yeah. And you do this, right? You square it, right? And then you integrate it and you find, of course, your S12 overlap, right? Which is 0. Right? It's a Kronecker. That's our crude assumption again. And so you simply have 1 plus 1 in here. So 2 times C1 squared must be equal to 1. You solve for C1 is 1 over square root 2. Okay. So with this prefactor, you have ensured that your total number of electrons in the system is good, is fine, right? You don't have more electrons than you're allowed to have, or fractional electrons or stuff like this, right? So this is the proper normalization, right? Now, how does the wave function now look like? Remember, the total wave function is the product of our molecular orbitals, right? So we multiply them with each other. Then you factor out the coefficients here. It's just 1 over square root 2 to the square is 1/2 times this thing, right? What is the electron density? Is our wave function squared, right? So we just take this. You'll find some terms drop and you can rearrange. This is the electron density of your pi orbitals in ethylene with the proper prefactors. Okay. So if you have the analytical expression for your p atomic p orbitals, you just insert it here, and within Huckel theory, you have the electron density that results from this. I think it's remarkable to see that, for instance, for arriving at equation 31, you did not need to know the alphas and the betas. Right? You needed the alphas and the betas to get your eigenvalues, right? And you needed these eigenvalues to get the right coefficients. But in this wave function, you don't, in this density, you don't see the alphas and the betas, so the Hamiltonians anymore. Right? But of course, the relative weights and the heights and so on, they result from the solution of the circular equation. All right, I hope this was clear, right? This is sort of the simplest example, two atoms, right? Ethylene, simple double bond. We now go to a slightly more complicated example, right? We'd like to look at butadiene. So 2 more atoms, 2 more electrons. So now we have 4 pi orbitals, right? So we have a HOMO -1, a HOMO, a LUMO +1, right? Now let's look at this. What happens, right? We can directly establish our circular determinant. This upper block here, the 2, this is what we had for ethylene, right? Now you add another carbon atom. That carbon, the 3rd carbon atom, interacts with the 2nd one through this beta. That's the on-site self-interaction of that carbon atom. And the 3rd carbon atom interacts with the 4th one through beta, right? That's it. That's the circular determinant, the circular Hückel determinant for butadiene. The whole thing must be equal to 0. Right? Now you can solve your quartic polynomial and find the roots. It turns out there's a nice little trick you can do which facilitates your life tremendously for solving this polynomial. And the trick is that you divide the whole determinant by beta to the power of the rank of the matrix, right? Here it's a 4 by 4. So division by beta to the 4 results in a division of every element of this matrix by beta, right? So if you define an X as your diagonal element divided by beta, then your beta elements all become 1. And your determinant has this simple appealing shape, which is sort of the simplest determinant you can solve, okay? So this makes your life much, much easier. So this is a trick I would strongly recommend you always apply, unless it's as simple as ethylene. All right, so what happens then? You get a polynomial, quartic polynomial, but the cubic term is missing. You see, the odd orders are missing. And you can do a substitution where x to the 4 is z to the 2. And then x to the 2 must be z, right? And so now this is a simple quadratic polynomial again, and you can use your usual formula for solving the z's, and then the x is the square root of the z's again, right? So this is some simple arithmetic tricks here. And then with this, you find that the eigenvalues correspond to these 4 numbers, right? We said homo minus 1. That's the eigenvalue of homo minus 1. We are in opposite signs. So, yeah, that's the eigenvalues. These are the x's, and then you put the x's in here and you solve for these eigenvalues here, right? So your various eigenvalues are alpha minus these x's times beta. All right, and now we get to the coefficients of Butadiene. But again, this is now the full system of equation, right? We keep these x's and we start substituting now, right? So you can see that if this must be 0, right, then your C1i must be minus C2i divided by this x here. So now you can replace your C1i, right, in the next equation. And you can also, for C4 and C3, you can do the same. There's only 2 coefficients, right? And then you substitute those back in and you find your third coefficient, right? And now you put in your eigenvalue for x. And so then you find that C31 is C21. So this whole thing here becomes 1. And C11 becomes this scaled down C21, right? And C41 becomes scaled down C21, right? And so this means if you imagine a set of 4 atoms, there is a coefficient. They just have one, the last coefficient we will get by normalization as always, right? But then in terms of relative weights, you see that F1 is a little bit scaled down. The 2 in the middle are a little bit larger. And then this one is scaled down again. So it's symmetric, right? Makes sense. And the one at the border are smaller than the one in the middle. So then you normalize and you find the exact coefficients here. And you see that again here in the middle you have the larger ones. Okay, so this is your there's no nodal surface, so this is the lowest orbital, right? The lowest lying orbital.
And it's a question. Yes. Why do we have to divide by beta to the 4 times these 4 beta terms? For me, it looks like the multiplication of the matrix 1 over beta. Yeah, it's the same.
Very good point. This is not a matrix. This is a determinant. Okay, a determinant. A determinant is a polynomial of the order of the rank. Okay, so if you want to change the determinant, if you want to get in there, you have to multiply with something like your variable to the power of the rank. Thank you. Good point. Yeah. I'm very thankful for comments like this. All right. So this is our lowest lying guy, right? No change of sign. In the outer 2 atoms, small factors, and then you have big factors and relative sign in the middle, right? So you can imagine something on the 4 atoms, right? A molecular orbital, which is this blub. The outer atoms contribute less than the inner atoms, right? Now you repeat this exercise for the next state, right? You use the x2 and the x3 and the x4 to get different, and each time you normalize and you get different MOs. And what do you see? Phi 2, you see a change of sign, right? The first two atoms have the same sign, and then the other ones, the second pair has opposite sign. Now it's the outer one which has a large magnitude, and the inner one has the small magnitude, right? Now we come to the third, right? What do we have here? We have positive sign, minus, minus, positive, right? So this is two nodes. And the second one, we only had one node, one change of sign. Now we have two changes of signs. On the two outer ones, you have really big ones, and then the inner ones are flipped and small, okay? And then finally, the highest lying orbital, you have a change of sign at every time. So you start out small, big, big, small, all right? So this, right, equations 41 to 44 are the molecular orbitals of butadiene. The eigenvalues are given by this, right? If you have to calculate the energy, remember ethylene, right? You have to put the 4 electrons in the two lowest lying eigenvalues, right? That means the two eigenvalues that gave you the two lowest lying states, right? 41 and 42, right? These eigenvalues are the, you multiply these eigenvalues with the occupation number, so with 2, and that total sum is then the total energy of the whole thing, right? Let's go to benzole. Benzole is more tricky because it's a ring, right? So imagine you start with one atom, you go to its neighbor, then second atom, you go to the third atom, fourth atom, the third atom, you go to the fourth atom, you go to the fifth atom, you go to the sixth atom, and the sixth atom has to go back to the first one again, right? And that's what these betas are for, right? That's this beta. So when far away you have a beta somewhere in your secular determinant, it means you're closing a cycle, right? You're closing a ring. So that's where these betas come from. And again, you can do the trick with the x, right? And you find this polynomial. And in this case, you can actually figure this out, that in the case of benzene, these will be solutions to this polynomial, right? You insert them and you will find these 6 eigenvalues. Equation 47, right? And so the total energy is 6 electrons filled up in the 3 lowest energies, right? So that means 6 times you have an alpha, right? In E1 and E2, E3, you have an alpha, so 6 times alpha, right? Then you have 2 times this beta, right? Gives you 4 beta, plus 4 beta from here gives you 8 beta. The total energy must be 6 alpha plus 8 beta. All right. What you also see is that actually E2 and E3 are degenerate. They have the same eigenvalue. Right? That's okay. The eigenvalue just happens to be the same. No problem. Right? Same for E4 and E5. Right? Also same magnet. So in terms of a molecular orbital diagram, you have the ground state, then you have the lowest state, then you have two occupied HOMOs, and then you have two unoccupied LUMOs, and then the highest lying unoccupied state. Now, remember, how much was an ethylene? We calculated it. Right? Here we calculated it. The energy is 2 alphas and 2 betas. Now, in benzene, you could expect that there are 3 ethylenes in there. Right? There are 3 double bonds in benzene according to Kekulé's structure. And we don't count the single bonds, right? We only care about the pi electrons. So what you see now is if we take 3 times the energy of ethylene, you would have 3 alpha and 3 beta. But if you consider the total energy of benzene, you have 6 alpha and 8 beta. So the delocalization in your pi system in benzene is worth 2 beta. Okay, that's something like the aromaticity. So that's what you gain by coupling your ethylines together, and it's just pi orbitals. Okay, no single bonds, right? The fact that you establish additional single bonds it doesn't count here, right? It's a pure pi effect, and purely a pi effect, pi electron effect. And so this is what how from a quantum mechanics perspective, how you can see aromaticity being manifested in cyclic aromatic system and cyclic conjugated systems. Right? Now, 1 beta is roughly 75 kilojoules per mole. So this is something like 150 kilojoules per mole. As we said before, this is not a covalent bond, right? You're still far from a covalent bond. That's half a covalent bond, or so you get, or even less than half a covalent bond, which you get just from aromatizing your system, right? But it's also not enough, right? Okay, so we have here the energies for benzole. Now we can do the orbitals. If you do this through the substitution, right? I encourage you to go through the exercise at home. You will find in terms of coefficients, normalized coefficients, you will find the following molecular orbitals. So let me show this here. So here are the molecular orbitals of the lowest one, right, with doubly occupied eigenvalue. This is, let's go back to the energy. This is worth alpha plus 2 beta, right? So the difference between these levels is always beta, right? Alpha, 1 beta, 2 beta. And here you have alpha minus 1 beta minus 2 beta going up, right? Okay, so let's look at this orbital 52, right? This orbital is the lowest one. Do you actually see my cursor? Okay.
Yeah,
so
we see it.
This lowest orbital corresponds to this, right? Every atomic orbital contributes the same amount, right? Same sign, there's no nodal structure. On the upper side, you have one sign, on the other one, you have, on the lower side, you have the other sign, right? Now, what happens at phi 2? You see that not all atoms contribute, right? So phi 2 must be what's actually here denoted as pi 3. I took this picture from the internet. Okay. Atoms 1 and 4 don't contribute to phi 2, right? So you see this here. They don't contribute. The node goes right through them. their contribution is 0. We talked about parity. Remember that the nodal structure matters. So here you go, right? And now what happens at phi 3, everybody contributes by the same amount, but there is a nodal structure, and this nodal structure must be going through the bonds, right? Not through the atoms, right? So we turn this, you see this here, for pi 2, you see that the nodal structure goes through the bonds. All atoms are still involved. Now what about phi 4 and phi 5? Again, for phi 5, that will be pi 4. 2 atoms don't contribute, right? You see this here, while in the other case all contribute, but you have 1, 2, 3 changes of sign, right? 3 nodes here. And finally, in phi 6, there's a nodal structure on every atom, right? You change sign on every atom. Okay. So I hope these pictures now, what you see here and the bottom, this is a typical molecular orbital diagram, right? So you have energy, you enter the different eigenvalues, and you make a drawing of the wave function matching roughly the relative size of each contribution and the sign for each atomic basis function. Right? This is what we call a molecular orbital diagram. All right, are there any questions? If that's not the case, let's stop now. Tomorrow, we will still analyze our results further. There are more nice things we can extract from Hückel, apart from energies and orbitals. And we'll talk about that tomorrow. And then I think within this week, we'll be hopefully done with Hückel. All right, I wish you a nice afternoon. Thank you so much for your attention.